In this video, let's determine the end behavior of each of these polynomials, and I'll show you a couple different ways that you can write it. So the end behavior of a polynomial is a way to try to describe what's happening as, well, one of the ways we say it as x goes to infinity. But basically, as we go to the right further and further and further, polynomials always head to infinity, well, assuming that they're at least degree 1. Because notice, like with a line is a very simple way to understand this. To the right, it's going up and up and up and up and up. And since it's straight, it's going to just keep going up forever. It's never going to like turn or come back just because of the nature of a straight line. And so like the question is, how do we write that? How do we describe the end behavior mathematically? One common way of doing it in algebra is by using the as x approaches infinity notation. So what we say is as x approaches infinity, y, or in the case of a function, let's just use, I called it L approaches infinity as well. And so I wanted to explain what all this means, but the arrow in math is always a symbolic representation of the term approaches. So it's sort of like equals. Equals means you x equal 5, right? You're at 5, a specific location. But as x approaches 5, x approaches infinity, what that means is we're concerned about what's happening as you get closer and closer. And the thing about infinity is, as we know, you can't reach infinity. There is no such thing as x equals infinity. X can't be equal to infinity because it's not a number. It's an idea of the end. And that's why we refer to this as end behavior, because there is no end. It's going to keep going. And so that's kind of the idea behind the notation. We describe as x gets closer and closer to infinity, meaning just as it goes to the right. That's just another way of saying it. What happens to L, or the y value? You could write y approaches infinity, or L, just because I've called this function L. But it's like as we move to the right on the graph, what's happening to the function? It's getting larger and larger and larger. It's going up and up and up. And so kind of another way of reading this as the graph goes to the right, the graph goes up. And since it doesn't have what we call a limit, polynomials are always unlimited, meaning that their end behavior always goes to either infinity or minus infinity. And if you're looking at the other graphs, notice that that's the same case, right? It's either going to go up very, very strongly or down very, very strongly. It doesn't like flatten out like this. Some curves, and actually when we look at rational functions, we're going to see examples of curves which do not go to infinity, but sometimes they have what's called an asymptote, where as you get larger and larger, it's leveling off or petering off, where we'd say that does not go to infinity. Polynomials will never do that. So they always go to either plus or minus infinity. And that makes it actually usually easier to figure out what's going on with them, because you know, well, it's either going to go up or down, and that's all we're trying to describe when we describe the end behavior. And you know, in a similar fashion, as x goes to minus infinity means, well, what happens as we go to the left, right? Because this is the negative x direction. As I go to left, it's good, you know, we're going to be going this way. And then if I trace along the curvature as we go that way, clearly it's going down. Instead of going up to heaven, positive infinity, it's going down into hell, negative infinity. And so this is how we could write it. L approaches minus infinity. And again, that would just be a way of saying, as we move to the left along the curve, the value of the curve gets smaller, or is going downwards forever. And you know, that would be kind of the end of how we'd write the end behavior. Another way that we write this in calculus is using what we call a limit. So I try to generally avoid this because limit notation, there's a lot of technicality behind the definition, which again, this is all stuff you're going to focus on in calculus, but it's all the ideas of what you're doing are the same as this. But we often say the limit as x approaches infinity of the function itself would be equal to infinity. So this would be an equivalent way of saying what I said right here, where LIM is just a shorthand for limit, and underneath the limit we put the location of where we're approaching. Limits always don't have an equal, they have an approach, just like in this as I wrote right here. And we read this as the limit as x approaches infinity, which would basically be saying, well, like, and limit, a lot of times certain graphs have what's called a limit. They're not unlimited. And, you know, you might say the limit is 5, meaning it's not going to surpass 5. But a function like a polynomial is not limited, it's unlimited, which is why it goes to infinity. All that being said, we would say that the limit of the function L, basically I can kind of imagine as x is getting larger and larger, it is not limited. And another way to kind of think about this, if you're more of a numbers person, you could think about, well, what if I start plugging in bigger and bigger and bigger and bigger numbers in for L of x? What would happen? Like, say, for example, I think about 100 or 1,000 or 10,000. Is this going to be limited or not? But like with a polynomial, you're always going to take x, multiply by 3/2 and subtract 3. So say, just for example, I plug in 1,000,000. Well, I would take 3/2 of 1,000,000, which is 500,000 times 3, which is 1.5 million, and then I'm going to subtract 3. Well, okay, that's 1,499,999,997. I don't know how many nines I just said, but you catch my drift. It's pretty much 1.5 million. Like, if you have $1.5 million, who cares if you lose $3, right? It's basically peanuts in comparison to the size of this term. But basically, it's not limited, because the larger and larger value of x I plug in, the larger and larger it gets. And that's, these are various ways of writing that. And the same goes for minus infinity, right? If I were to plug in something very, very negative, largely negative, small technically, it would get really, really, really negative, so it would get smaller and smaller and smaller the larger of a negative that I plugged in. And looking at quadratics, and another thing about linear functions is the degree also affects the nature of the end behavior, which is something I wanted to show you guys in this video. So looking at the next three, let's try to do those a little bit faster. With the quadratic, notice that to the right it goes down, and to the left it goes down. So the end behavior in both directions is actually minus infinity. So we'd write that as x approaches infinity. What did I name this function? Q for quadratic. Q approaches minus infinity. And as x approaches negative infinity, Q also approaches minus infinity. And notice that they are both approaching negative infinity, because again, this is kind of like saying as I go to the right, the value of the function is going down to minus infinity. It's going to get smaller and smaller and smaller. And same as if I go to the left. Technically it's increasing, but if I'm viewing it from right to left, which is not how we define increasing, it's going downwards. Or basically you could say, well, where's the arrow going on the right hand side? Is it going up or down? That's how you determine whether it's plus or minus infinity. Both of these are going down, so they're both going to minus infinity. And anyways, and notice that's true about parabolas, right? One thing about parabolas is the end behavior is always going to be in the same direction. When it's going upwards, both are going to be positive infinity, both tails. And when the leading coefficient is negative, both end behaviors are going to be negative because the parabola is facing downward. Now, notice the thing about the degree 3 and degree 4 polynomials. Notice that the degree 3 polynomial has opposite end behaviors. To the left, it's going down, and to the right, it's going up. So again, if we're going to write that out, as x approaches infinity, to the right, it's going up. C goes to infinity. And as x approaches minus infinity, C also approaches minus infinity because it's going down to the left. With the quartic function, notice that both end behaviors are going in the same direction as x. Oops, move my tablet. As x approaches infinity, aka to the right, the function q is going also upwards, and as x approaches minus infinity, q is also going upwards. In both directions, it's going to positive infinity. And the thing I wanted you to notice about the degree here is that if the degree of a polynomial is an even number, like 2 or 4, notice that the end behavior always goes in the same direction, like a parabola or the degree 4 one below. And there's a mathematical reason why. It has to do with the fact that the leading term, since it's an even power, the leading term in a polynomial always, what I like to say is it dominates the end behavior. Because, like, say I'm imagining plugging in a number even as big as, say, 1,000 into here. if I think about the implications of plugging in a big number like 1,000, I could think about term by term, or even just 10. Let's just use 10 because 1,000 is going to be really irritating to try to raise to all these powers. But if I were to plug in 10, 10 is pretty easy. And I don't know if you ever noticed this about polynomials. It's kind of a cool feature, is if you plug in 10, what will happen is each term is just 10 or 100 or 1,000. It's a group based on that number. So like this term, well, since there's a fraction, that technically it doesn't work like that, but notice if I plug in 100 or 10 in here, this term would be minus 50, and this one would be 10 cubed, which is 1,000. And so, well, this one's missing an x squared term, so again, it doesn't exactly follow what I'm saying, but if you catch my drift, it's like, well, this would be 3,000 minus 50 minus 1. So the value of this polynomial will be 2,949. And you can do math with polynomials pretty quickly if you're using 10, just because of how it works. It sort of reads the digits of the number. Or like over here, this would be if I plug in 10, this would be negative 30, negative 100, positive 2,000, and this one would be, well, 1/2 of 10,000. But the whole point here is that, the whole point of what I'm trying to get at is not that, but it's that when I plug in large numbers, the leading term is always way, way larger than the rest. And that's why it's so important and why it affects the shape the most. Like say I plug in even just 10, this term would be in the 10,000s, well, technically 5,000, whereas the rest are a lot smaller. And if you plug in bigger and bigger and bigger numbers, say for example, I plug in 1,000 in here, this would be 1,000 to the 4th power. That would have 12 zeros in it, which is what? Million, billion, trillion? Is that 12 zeros? Billion is 9 zeros. Yeah. So I believe that would be, in the trillions, whereas this would be smaller by a factor of 3 zeros. It would be like trillions, billions, millions, thousands, ones, and it magnifies so much greater. And so it's kind of like the rest of the function doesn't even matter because we'd have half of a trillion, and this would only be 2 billion. Now, if you're not great with big numbers, it might be kind of hard to follow what I'm saying, because a lot, like in my experience, a lot of people have trouble with just really, really large numbers. And that just really comes from understanding the system of, basic place value and how polynomials fit into there. So sorry if I'm getting like really off topic right now, but if you see what I'm saying, as we go to the right, the leading term is going to really be the big effect on what the shape is, which is why when it's an even degree, both directions is going to get really big. And notice, because this is positive, because it's positive, this term is basically going to tell us what's happening. It's going to go to infinity in both directions. And with this one, since the leading term had a negative leading coefficient, they were both going down. So you can actually predict the end behavior based on, if it's even, it's going to have the same sign as the leading coefficient, and they're both going to be in the same direction. Whereas if you have an odd polynomial, notice that the end behaviors are always opposite. And the direction of the end behavior follows the sign, meaning if it's to the right, it's going to be positive if it has a positive leading coefficient. And that's just kind of like slope, right? If it's positive slope, it's going to go up to the right. But if it's a negative slope, it's going to go down to the right. And notice that the polynomial is degree 3, very similar. It's not a line, but it has the similar end behavior where one direction is up, the other is bottom. And it's notice it's paired up because it's a positive leading coefficient. They're both positive and negative simultaneously. Whereas if you had a negative leading coefficient, this would all be swapped around. Anyways, this video is getting way too long. In the next video, I want to say there is a shortcut for figuring out the end behavior, which is kind of using all these ideas I've been talking about. But that will wrap this one up.